Right, last class we left off talking about partial pressure from mole fraction. So mole fraction being what fraction of the total mixture is the thing that we care about. So if it's 78%, like nitrogen, 78% of our air, then just turn that 78% into the fraction form, 0.78, and that's the mole fraction. We can also calculate it based on a total amount of moles of gases. So here's an example of a problem that we might get in that line. So some flavor text: to prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. Basically, they don't react, and they can exclude air, push air out, and other reactive gases out. So a chemical engineer places a mixture of noble gases consisting of some grams of helium, some grams of neon, some grams of krypton in a piston cylinder assembly. So we've got like a container with a piston that can move up and down. At STP, calculate the partial pressure of each gas. So we are looking for partial pressure of each gas. We are told that it's amounts of helium, neon, krypton, and that the cylinder is at STP. And the STP is critically important here. I guess it's not. Yes, it is critically important. Who remembers what STP stands for? Like, just what do the letters correlate to in terms of words? Standard, temperature, and pressure. So STP, standard, temperature, and pressure. And who remembers what those temperature and pressure are? 0 degrees Celsius and 1 atmosphere. So the 1 atmosphere part of this is really important since we are asked for partial pressure. So that 1 atmosphere is very important. The other thing that's important is the amounts of each of the gases that we're given. So we can convert these grams to moles for each of our gases. So for helium, divide by our molar mass. Get out the calculator. Flip my pencil. And 1.375 moles of helium. With our neon, 15.0 grams neon, divide by the molar mass, 20.18. We've got 0.743 and some other stuff, moles neon, and then the last one is the krypton. And we also divide that by its molar mass. This one's 83.80. So we've got 0.417 and some other numbers after that, moles of krypton. The reason that we're finding the moles of each of these is because, like we saw on the previous slide that we looked at a little bit, very briefly, right, we can calculate the partial pressure by multiplying the mole fraction by the total pressure. We know the total pressure because we were told that it's STP. So we know the total pressure is 1 atmosphere. If we know the mole fraction, which is related to the number of moles that we have, then we can calculate the partial pressure from that. So we need to add up all of our moles. So our total moles is just the 3 numbers that we got added together. 2.5 and some change moles. So for each of our gases, our pressure of helium, our pressure of neon, our pressure of krypton, it's going to be the mole fraction times the total pressure. We said our total pressure is 1 atmosphere because we're at STP, so we just need to figure out what the mole fraction is. So that's going to be the moles of helium divided by the total number of moles. So that's 1.375 over 2.53 times 1. So our partial pressure of helium is 0.54 atm, 0.542. And the process would be the same for the other ones. Put the calculation in wrong. Okay. So for our neon, we're taking the 0.74 and change, dividing it by the 2.53 and multiplying it by the same total pressure of 1. So this one is 0.293 atmospheres. And then our last one, we're taking the 0.417 moles of krypton, dividing it by the total moles of gas, and then multiplying that by our P total, which is 1. So this is 0.165 after we round for 3 sig figs. And if we wanted to check that we did everything correctly, we could also sum up all of our partial pressures, and it should be about 1. It might be a little higher, a little lower, depending on how things rounded out. Sometimes it doesn't always sum to 1. Questions about any of that process? Okay. A gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3 atmospheres. What are the partial pressures of helium and neon? Our options are partial pressure of helium is 2 atmospheres and neon is 1. We've got the other option of 1 atmosphere for helium, 2 atmospheres for neon, and 1.5 atmospheres for both. Any guesses? So we know that the total pressure is 3 atmospheres. We also know that we've got an equal number of moles of helium and neon. It doesn't say how many, so we can just try something. Let's say that we've got 1 mole of helium and 1 mole of neon. Our partial pressure of helium is going to be the mole fraction of helium times the total pressure. And the mole fraction is going to be the moles of helium divided by the total number of moles. So 1 mole over 2 moles times our total pressure. So it's going to be 1.5 atmospheres. And it's going to be the same thing for neon. It's going to be 1 mole of neon divided by the total of 2 moles of gas times our total pressure of 3 to give us 1.5. Oh. So the correct answer here would be C. Let's say that we've got a sample of hydrogen gas, H2 gas. It's mixed with water vapor. The mixture has a total pressure of 755 torr. The water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? So we've got a bunch of numbers that are given to us. It would be helpful probably to label them. So the first thing that we are given is this 755 torr. That's our total pressure. So P sub T O T, 755 torr. And our water vapor has a partial pressure of 24 torr. So our P sub H2O is 24 torr. We look back at the problem. What amount in moles of hydrogen gas? So we're trying to find moles of hydrogen gas. That would be N sub H2. That's what we're looking for. And we're also given some other conditions, 1.55 liters and 298 Kelvin. So liters is a unit of volume, so 1.55 liters for our volume, and 298 Kelvin is our temperature. If we're trying to get to the number of moles of H2 and we've got volume and temperature, what's an equation we might be able to use to get number of moles? What's an equation that has N in it? Yeah, our ideal gas law. So PV equals nRT. So PV equals nRT might be able to get us to this number of moles. If we rearrange PV equals nRT, N is PV over RT. We have temperature, we have volume, we are missing pressure, and R is our gas constant, so we also have that. So how can we get the pressure of our hydrogen gas? We've got a couple of pressure values. We just don't have the pressure for the hydrogen gas. We've got the total pressure, we've got the pressure of water. If our total pressure is 755 torr, and 24 torr of that is from water, what's the rest of the pressure from? Hydrogen. So we're told in the first sentence it's hydrogen gas mixed with water vapor. So this is Dalton's law of partial pressures is what we're using here. So P total is equal to the pressure of the hydrogen gas and the pressure of the water. So all the gas components, their pressures add up to equal the total pressure. So with our P total and our pH2O, P total minus pH2O equals pH2. So just rearranging our specific version of Dalton's law of partial pressures. So the pressure of the hydrogen gas is the 755 torr minus 24 torr So we've got a partial pressure of hydrogen of 731 torr. And then we would have to put it into our N equals PV over RT. To do that, we also need to convert to atmospheres. Doing the laziest conversion here. We could also use an R value that has units of torr instead of units of atmospheres if we had that on hand or knew it or looked it up. Any questions about the rest of the problem? The steps that we use to get to solving PV equals nRT? Okay, then we'll just finish writing out the calculation. .0.06096, repeating or continuing more stuff, moles. Partial pressures also plays a role in deep sea diving. This is mostly just for fun information. So if you go diving, especially if you go deep sea diving, when you go and do some scuba, you're going to be breathing a mixture of compressed air. If you're going like shallow depth, you'll just have a tank of compressed air on your back. It's compressed partly so that it'll still inflate your lungs, because you've got the added pressure of the water around you. However, if you are breathing this at high pressures, that increases the pressure of the oxygen in your lungs, even if it's the same ratio mixture, just because we've jacked up the pressure, the partial pressure of the oxygen gets jacked up too. And that can get to a point where you start to experience oxygen toxicity. So if you get too much oxygen in your bloodstream or in your air that you're breathing, that can cause some wacky stuff to go on in your body. That's about 1.4 atmospheres of oxygen. And hypoxia occurs when your oxygen pressures are too low. So this is typically like if you're going up to Everest or something, or other really high elevations, or if you're just in a low oxygen environment. You can also run into issues of not having enough oxygen. Other issues that can happen if you go and do some scuba diving is nitrogen narcosis. So if you get nitrogen pressures above 4 atmospheres, so you'd have to be relatively deep in terms of diving to get 4 atmospheres of pressure, that can lead to nitrogen narcosis, which apparently is similar to alcohol intoxication. So if you've been drunk, apparently nitrogen narcosis is similar, and I imagine that's a very unpleasant feeling to get suddenly when you're 50 meters underwater or more. So to avoid that, deep sea divers instead have a mixture of gases called heliox, which has oxygen and helium in it. So the heli part of heliox for helium, the ox part for oxygen. And since helium doesn't give you the same nitrogen narcosis, that's a way of getting around that issue. All of this to set up for this problem. A diver breathes a mixture, a heliox mixture. So this is, again, helium and oxygen. Heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be? For the partial pressure of oxygen to be 0.21 atmospheres. Does anyone remember what our symbol for mole fraction is? What it looks like? It looks like an X. So our mole fraction of oxygen is 0.050. And our partial pressure of oxygen is 0.21 atmospheres. And we're trying to find total pressure. Does anyone know an equation that has all three of these variables in it? I don't think we have a name for it, just trying to direct us to think about where have we seen these before. The where we've seen these before is in this, I'll give them all the label O2. So the partial pressure of a gas is equal to the mole fraction of the gas times the total pressure. That's the equation where we would have seen this before. We've typically been using this, we used this earlier where we had mole fraction and the total pressure. This time we've got the partial pressure and we've got the mole fraction and we're finding the total pressure, so we have to rearrange a little bit. So dividing both sides by the mole fraction and then flipping left and right. Our total pressure is our partial pressure of oxygen divided by our mole fraction of oxygen. So our partial pressure of 0.21 atmospheres divided by 0.050 so our total pressure would have to be 4.2 atmospheres. So this would be like 32 meters underwater. Questions about any of that? Arguably, the hardest part of a lot of these problems is just knowing which formula is the correct one to use. All right, so one of our previous problems alluded to the fact that we can collect gas over water, which I'm trying to remember if we're doing that today or if we're doing that next week in a variant. But it's common to have a lab in Gen Chem where you collect gas over water. So the example here is that we've got zinc metal dissolving in hydrochloric acid. And when it does that, when the zinc dissolves in the HCl, it produces hydrogen gas as H2. And you can force that H2 into a beaker or some other thing that's turned upside down that is originally just full of water. And the bubbles will all float up to the top and push the water out. So they displace some of the water. And that means that we've got just hydrogen gas trapped up in this airspace. However, because we also have water present, some water vapor is going to get in there as well. So we've got a mixture of hydrogen gas plus water vapor that's in here. But it excludes the nitrogen, the oxygen, the other gases that are normally found in air. So it's a pretty convenient way of catching gas. With this type of setup, if we were doing this in the lab, if we were collecting this hydrogen gas in the lab, it's important if we want to know how much partial pressure of hydrogen we have, so we know how many moles of hydrogen gas we have, for example. It's important that we know the vapor pressure of water. And fortunately, people have studied water a lot, and so we have tables that show the partial pressure of water at a bunch of different temperature values. And they can get more granular than this. So if you needed like 1 or 0.1 degrees Celsius increments, that information is probably out there somewhere. So the vapor pressure of the water is the partial pressure. This is specifically at equilibrium. We're not going to talk about that yet. But the vapor pressure, how much water is in the vapor phase. And so we can use our law of partial pressures to calculate some of that information. So an example of using that, we've got a sample of acetylene, a gas that's often used for welding. It's collected over water. So our gas mixture has acetylene, C2H2, and water. So those are the two gases that we have present. The total pressure is 738 torr, so PTOT, 738 torr. Volume is 523 milliliters. The temperature is 23 Celsius. The vapor pressure of water is 21 torr. And we want to know how many grams of acetylene are collected. So we're looking for mass of acetylene, C2H2. This is similar to the problem that we solved previously. It's the last problem that we solved. So we've got V and T. We've got a couple of P values. So this should hopefully evoke ideas of PV equals nRT. So we need to find the number of moles to get to the mass. So we need moles to get to mass. To get to moles, we can use PV equals nRT. We rearrange it. N equals PV over RT. Like before, we've got volume that was given to us. We've got temperature also given to us. We don't have pressure, so we'll have to find a pressure value for our C2H2. To get that, since we know that we've got a mixture of just acetylene and water, and we've got the total pressure and the partial pressure of one of the gases, we can use this Dalton's law of partial pressures. To find our partial pressure of the acetylene. So if we subtract our partial pressure of water from our total pressure, that'll give us our pressure of the acetylene. So 738 torr minus 21 torr equals our pressure of acetylene, which is 717 torr. So now that we've got our pressure, we've got all the tools that we need to find the number of moles of acetylene. Questions on how we got here? Okay. So our N equals pressure. I'm going to skip the unit conversions to save time. So our atmospheres are 0.523 liters. R is what it usually is with all of its units. And assuming I did that all correctly, 0.02 and some change, because I ran out of space, moles C2H2. And we multiply that by the molar mass of C2H2. Which is 26. So we collected about half a gram in that tiny little corner of the screen. So the ideal gas law stuff at the end is newish, the converting moles to grams. We've been doing that. The big focus of this is really just that we've got a mixture of gases. The partial pressures add up to the total pressure, so we can find the partial pressure of the gas that we care about. I'll give you one to try. You'll need the table from before, so I'll go pull that number for you real quick. Okay, so our pressure of water I think it was 23.78. So looking at this table of vapor pressure of water, our temperature in degrees Celsius, and our pressure in millimeters mercury, or torr, we've got 25 degrees Celsius for our temperature, so our pressure is 23.78. All right, so the first part of solving this problem, obviously there's a lot of text. Most of it's not important. I would say maybe half of it isn't like that important. First sentence, definitely not really. It's just flavor text, so it's just extra information. Hydrochloric acid reacts with metal. It produces hydrogen gas, which is then collected over water. So this is important. It lets us know that we've got hydrogen gas. Since it's collected over water, that means we also have water present. So we've got a mix of H2 and H2O gases. What that means is we've got a two-component mixture of gases. One of them is hydrogen, which is what we want to find more information about. The other one is water. And since we know the characteristics of water, we were able to look up for this temperature that at 25 degrees Celsius, the partial pressure of the water is 23.78 torr, or the vapor pressure of water is 23.78 torr. And we know Dalton's law of partial pressures. So P total equals pressure of component A plus pressure of component B plus pressure of component C plus so on and so forth until you run out of components. We've got a two-gas mixture, and so it's just two things. So our total pressure is equal to the pressure of the H2 gas plus the pressure of the H2O gas. And we have the total pressure, it's 742, and we also have the 23.78 torr, that's the pressure of our water. So we've got PTOT, we've got pH2O, so we can find pH2. So a little bit of rearranging, we find that pH2 is 742 mmHg minus, I gave it to you in torr, it's the same as millimeters mercury. minus 23.78 mmHg. So our partial pressure of hydrogen is 718.22 millimeters of mercury. Any questions about that part of the problem specifically? Great, so if you were stuck there, we're past it, so go ahead and give the next part of the problem a try. All right, next part of the problem. We've got pressure that we just found in the previous part. 718.22 mmHg. We also have volume and temperature. Our volume being 154.4 milliliters, our temperature being 25 degrees Celsius. And we're looking for mass of hydrogen gas. To get mass of hydrogen gas in milligrams, because we want to do the most work possible, we first need the number of moles. So we need to find N. So hopefully this also evokes thoughts of PV equals nRT. Look at that, it's PV equals nRT again. So nRT equals, N equals PV over RT. We found pressure from the first part. We also have volume and temperature, and R is what it usually is, which is 0.08206 latum per molk, liters atmospheres per mole Kelvin. We've got a little bit of a problem because the units in our R value are liters, atmospheres, moles, Kelvin. We've got millimeters, mercury, milliliters, degrees Celsius, and we're finding moles. That means we get to do 3 unit conversions. So we have to convert our pressure to atmospheres, which is dividing by 760. Our volume we get to divide by 1,000, because there's 1,000 milliliters in 1 liter, or 1 milliliter is 1,000th of a liter, whichever way you want to write it. And for our temperature, we're adding 273.15. So we'll do these real quick. Some of these you don't necessarily have to have the conversions memorized, but you can maybe see how it could be helpful to not have to go hunting down conversion factors every time you get to a problem. Okay, so these are our new values, our new unit values for pressure, volume, and temperature. So we can plug in to N equals PV over RT. So we've got P and V on the top. We've got our R value. With all of its units. And we've got also down there 298.15 Kelvin. Everything except for the moles cancels, and the moles gets flipped up to the top because it's on the bottom. So we multiply everything on the top, divide by everything on the bottom, get 0.0596, and some change moles. Just as a reminder, it might be helpful for this problem to remember to put parentheses around the numbers on the bottom, unless you're dividing by each of them individually. So that's our moles, and then we would have to multiply by the molar mass of hydrogen gas. What's the chemical formula for hydrogen gas? Is it H? Zero zero 596. Thank you. There's a certain animal that needs oats for clear brown eyes. Allegedly. Does anyone remember what that animal is? Horses. What letter does horses start with? And why is that significant? It's a diatomic element. So hydrogen gas is H2. I also labeled it as H2 previously. So this is H2 gas, and so it's got a molar mass of 2.016 grams per mole, 2 times the molar mass of one hydrogen. So when we are getting to the grams for our almost final step, we're multiplying by basically 2. So it's 0.012 and some change grams H2. Are we done? Almost. The only thing that we're missing is the problem specifically asked for the mass in milligrams. So we get to do one final conversion to milligrams, so we multiply by 1,000. It's 12.0 milligrams of H2, and now we're actually finally completely done. Possibly in more than one sense. Questions about any of the parts? That's about as complicated, I think, as this type of question can get. Most of your exam questions will be less involved than this, because obviously this takes a long time. Great. There's other ways that we can do things with gases. So we've looked at reactions previously. We can also do reactions with gases. So we're not always going to be reacting things that are in solid or aqueous or liquid states. Sometimes we will be using gases. In reactions that involve gaseous reactants or products, it's more convenient to specify the amount of gas in terms of usually like liters or a volume of the gas rather than the mass of the gas, because gas is hard to weigh. It's hard to like wrangle all your gas molecules together and set them on a scale, because they have a tendency to float away and get scattered all about. So for reactions with gases in them, it's a lot more convenient to use volume as a way of measuring them. So some of our reactions that have gases might look something like this. So our solution maps, for a lot of our problems prior to this, we would have been starting with some mass, going to an amount in moles, using our stoichiometry, our balanced chemical reaction, the coefficients, the ratios of those two things, to convert, figure out an amount of some other chemical in moles, and then converting to the mass. However, since we're working with gases, oftentimes you'll be supplied pressure, volume, and temperature of a gas, and then we can find the number of moles. with N equals PV over RT. That'll get us to the amount of moles of that gas that we have. We'll still be doing a stoichiometry step in the middle, or ratio step, from our balanced chemical equation. And then that'll get us to an amount in moles of some other gas. And then we can calculate pressure, volume, or temperature, whatever we want of that gas, using PV equals nRT. We could also switch up this last step. We could go from moles to mass. That would also be an option, in which case we would be using molar mass instead. So we've got a couple of different ways that we can work around, swap out some of these steps. The stoichiometry part, anytime we're doing a reaction, we're always going to be doing the stoichiometry, that ratio step in the middle. But the rest of the parts are fairly interchangeable. And just as a reminder, I think we covered this, we talked about this, at STP, 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of any gas is 22.4 liters. So occasionally that will be helpful to invoke or to use. Let's see what this looks like in action. In the following reaction, 4.58 liters of O2 was formed at a pressure and a temperature. We want to know how many grams of silver oxide decomposed. So as is often the case with gas problems, it's helpful to have our variables labeled. So our pressure, 745 mmHg, which is the same as torr. Our volume is that 4.58 liters that we saw earlier. And temperature is 308 Kelvin. We're going to be using PV equals nRT. We've got pressure, we've got volume, we've got temperature. And R is a constant, so we will be solving for N, the thing that we don't have. So we're going to see our old friend. We've seen this many times before. N equals PV over RT. We'll have to convert our pressure so our pressure is 745 divided by 760, which is about 0.98 atmospheres, times our volume of 4.58 liters, divide by our R value, and multiply in the bottom by our Kelvin. Liters cancel, atmospheres cancel, Kelvin cancels, moles flips to the top. So we had 0.1776 and change moles of O2. So that's the gas part of the question. So this is the amount of moles that we started with. We care about, or we are interested in finding the grams of silver oxide. To get from moles of oxygen to grams of silver oxide, we would need to first get to moles of our silver oxide. We can go from moles of O2 to moles of Ag2O with our balanced chemical equation. So we will produce 1 O2 for every 2 Ag2O that we put in. We can pull those out to make a ratio. 2 Ag2O equals 1 O2. And that's a conversion factor. So starting over here on the left with our 0.17 and change moles O2, we put the 1 O2 part of our conversion factor on the bottom. And the 2 Ag2O on the top. This makes our O2s cancel. So the moles of our silver oxide is 0.355 and change. And our goal is to get to grams Ag2O. How can we get from moles to grams? What do we need? Molar mass. So we'll have to calculate a molar mass. We've got 2 silvers, 1 oxygen. Silver has a molar mass of 107.87. So 2 times 107.87 and then add about 16. So it's 231.739 grams per mole. Grams over moles. So we multiply our molar mass and our moles. And we must have had 82.3 grams of silver oxide, at least. Any questions about that? All right, another one. This one's potentially shorter. How many liters of oxygen are required to form 10.5 grams of H2O? What are we looking for in this problem? What are we trying to provide? Liters of oxygen, and we were given 10.5 grams of H2O. We were also given a balanced chemical equation. And what's the last piece of important information that we were given? Yeah, we are at STP. So we're going to be starting with our grams of H2O. We are trying to get to liters of O2. What can we do with our grams of H2O? What can we convert that to or calculate from that? Yeah, we can calculate moles of H2O. We've got a balanced chemical equation. Chances are almost 100% probably that you're going to use your balanced chemical equation at some point, and we need moles to use our balanced chemical equation. From moles of H2O, what can we get to? What chemical are we trying to end in? Our answer is going to be for oxygen, for O2, so we need to change our chemical out. So figuring out the moles of O2. And that's going to be using the ratio from our balanced chemical equation. So 1O2 equals 2H2O would be our equivalency, our ratio that we would use. And then from moles of O2, presumably we can get to liters of O2. That grams to moles, of course, we're going to be using molar mass. Any questions or confusions about our solution map? We'll talk about what that last arrow is when we get to it. Okay, so starting with 10.5 grams H2O, we need to divide by our molar mass to get 2 moles. So the grams goes on the bottom, the moles go on the top. 10.5 divided by 18.015, 0.582, and some other stuff, moles of H2O. Then we need to use our stoichiometry step, our ratio from our balanced chemical equation. The 2H2O part goes on the bottom, so our units cancel. The H2Os cancel out. So for every 2 moles of H2O that we would have produced, we would have had 1 mole of O2 to start with. So we divide by 2, and this tells us how many moles of O2 we must have had, which is 0.291 moles O2. To get from moles to liters, we've got some options. You might think PV equals nRT, and that can work. We're told that we're at STP. Who remembers what STP conditions are? Zero degrees Celsius, 1 atmosphere of pressure. So we could solve it plugging in 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere into our PV equals nRT. Since we've got N, we've got T, we've got P, so we could solve for volume. However, we might also remember that gas at STP has 22.4 liters per mole, which would let us just skip past the PV equals nRT part. I mean, it's kind of included in there, it's incorporated in there, but this lets us do this in one step without having to rearrange our ideal gas law. So either of those two options works. I'm going to do the 22.4 liters per mole because it's just easier. So we have 6.53 liters of oxygen that we would need to make 10.5 grams of water. So some of the important things you should know from this, like that we used in here, right? We want to know PV equals nRT. You should have that memorized. You also need to know what standard temperature and pressure are. Freezing cold, 0 degrees Celsius. At the beach, 1 atmosphere. Or just 0 and 1. And it would also be helpful to remember that gas at STP has this 22.4 liters per mole, because it lets you skip through some calculations. It's not strictly speaking absolutely necessary, but it is definitely helpful. All right, and then our last little bit of stuff that we'll talk about today, kinetic molecular theory. I've been alluding to it a little bit in some of the previous slides, especially when we were talking about the simple gas laws. So this is a very simple model for gas behavior, kinetic molecular theory, KMT. So in kinetic molecular theory, our gas is modeled as a collection of particles, molecules, or atoms that are constantly moving. This is just how gas behaves. But we're looking at a slightly simplified version. So there's some points to our kinetic molecular theory that are important. The size of the particle is negligibly small. It doesn't take, there's just a bunch of empty space is basically what we're saying here. So they've got room to travel before they run into another particle. They're not crammed so close together that they're constantly running into stuff. They're relatively spread out. So there's lots of empty space relative to particle size. And this is generally true. So they're not all crammed together so that they're basically like a liquid. They've got lots of room that they can fly around in their straight lines. So small particles relative to the amount of space. The kinetic energy of the gas particles is directly proportional to temperature in kelvins. So high temperature means high average speed. So hot gas, if you increase the temperature, the gas is going to move around faster. If you decrease the temperature, the gas is going to move around more slowly, just kind of on average. And that's directly proportional to the Kelvin temperature. Anytime that there's a collision between two particles, they just bounce off. They're not like sticking together when they hit. They're not repelling each other extra. If you think of like playing pool, like billiards balls bouncing off of each other, that's sort of the thing we're thinking about here. They're not sticky, they're not covered in felt, they're just bouncing off harmlessly. So there's no energy lost in collisions, is what perfectly or completely elastic is talking about here. They just bounce off. So we're ignoring friction and a bunch of other stuff that make things more complicated for us. This is just more talking about elastic collisions. So some of the things that kinetic molecular theory, things that arise out of kinetic molecular theory is gas pressure. So because our gas particles are constantly in motion, gas particles are constantly moving, they strike the sides of a container. And they're really small particles, but when they strike the side of the container, that's a small amount of force. Think of it as like little tiny punches or pokes from the molecules. And because we've got lots of gas particles, many particles, billions upon billions of particles, they're constantly running into stuff, and that sum of all those tiny little forces adds up, and it's applied over some area, and so that's pressure. So it's the particles that add up to produce pressure. This is important because if we think of ways that we can increase the force, then that will also increase the pressure. And likewise, if we can think of ways that we can decrease the force, decrease the number of collisions, decrease how hard they're hitting. That will also decrease the pressure. And I think I'll stop there, just for time's sake. Any questions before we stop? So anything up through kinetic molecular theory so far could show up on our exam next week.